Well, I've no idea whether today is a typical day in the life of Sir Clive Sinclair, but he is a bit of a mega star of the micro, so it's perhaps not very surprising that Micro Mega have produced this little game for the Spectrum, based on a hypothetical day in the life of Sir Clive, in which he gets up to all the things you'd expect him to do, going to the bank to deposit large sums of money, going to the palace to get knighted, and rushing around London in his C5, although I've always rather thought that he was more of an Aston Martin or a Porsche man myself. Well, that's their idea anyway.
Hello cave dwellers. Sir Clive certainly was taking bags of money to the bank, and we continued to fill them as the ZX Spectrum became ever more popular, not least because developers found new and exciting ways to present games to us. It was never Sir Clive's vision to create a games machine, and it was capable of so much more, but there's no denying games were a key part of the Spectrum's success, and second only to gameplay in a good game is of course graphics, and that's the topic of our video today. The unique way in which the ZX Spectrum put pixels on our screen, the tricks, tips, hacks and techniques to the ZX Spectrum's Ghetto graphics. During our tour of the Spectrum in the first episode, you would have noticed that it's lacking in custom hardware to deal with graphics. With the exception of the ULA to output video on the screen, all graphical functions are handled by the Z80 CPU. This is in stark contrast to, say, the Commodore offerings, in which custom chips were included for just such a purpose. With the CPU dealing with both graphics and game logic or other functions at the same time, it did of course require a degree of trickery to get the best out of it. While it was Sir Clive's intention to build a general purpose machine, most of those purposes he expected to be text based, and that's reflected in the way the machine is set up. And to understand why, we'll start with the memory. The ZX Spectrum, lacking in its custom graphical chips, is also lacking in dedicated video memory chips. A portion of the computer's RAM is set aside for screen duties. Every part of the RAM has an address so that the other chips can address the memory and read or write data to it. The Spectrum's memory addresses look like this, and we're interested in two areas in particular: the memory addresses assigned to the display file and the attributes. The total size of the display file section of the memory is 49,152 bits, and that's no coincidence. The resolution of the ZX Spectrum screen is 256 by 192 pixels. Multiply those numbers and you get the same, 49,152. In other words, there's one bit of memory for every single pixel on the Spectrum screen. Set a bit to 1 in the display file and a pixel appears, set it to 0 and it disappears. We therefore have complete granular control of exactly where pixels appear on the screen, as you might expect. And you also might expect that memory space to run from the top left to the bottom right of the screen. Here's a program running that sets every single bit in the display file to a 1 from the start to the finish of the display file. Instead of running from left to right, top to bottom, you'll notice that there's a gap between each line as it works through the display file. The display file also seems to be split into 3 sections, filling each one at a time before moving on to the next. Curious. We'll come back to that shortly. So far we can put pixels on the screen, but they contain no colour information, and that's where the next part of the memory map comes into play: the attributes. The attributes section of the memory is 6,144 bits long, but it's impossible to describe a colour in a bit with a 1 or a 0. Therefore it's grouped into 8 bits, 1 byte per attribute. We therefore have 768 bytes in this memory space, 768 attributes with which to colour the screen. An attribute grid of 32 by 24 blocks. So how does that work? We've got over 49,000 pixels we can put on the screen, but we can only describe colour in 768 units. How do we colour the individual pixels? And the answer on the ZX Spectrum is that you can't. Let's put data in all 768 attributes and you can see the colours appear on the screen. 768 8x8 pixel squares, each one an attribute. A massive oversight, you may be thinking, in the computer's ability to produce coloured bitmap graphics. But this was a time when computers, especially in the business world, were measured by their ability to draw rows and columns of text. In that context, each of these attributes fits perfectly around a character on the screen. And within each byte that makes up an attribute, we can define both the background colour, the paper, and the foreground colour, the ink. So we suddenly have a very easy and flexible way of presenting text on the screen. Further bits within the attribute byte allow us to enable brightness, which gives another level of intensity to each colour in the palette, and we can also set a flash bit to make the colours flash. When you combine the way that the attribute memory space is laid out, and look back at the way the display file was laid out, you realise that those lines were drawn with 8 pixel gaps between them. So the display file was stored again with text in mind, and to make it more logical for programmers to navigate around that memory space when making their programs, in the context of rows and columns of 8x8 pixel text characters. Furthermore, it was split into 3/3, each of which represents 8 rows and 32 columns of text. What all of this means, of course, is that trying to colour in the bitmap image that you've drawn in your display file using 8 pixel by 8 pixel colour blocks is akin to telling an artist he can only colour in his line drawing with a potato. So did these limitations stop developers from making games for the system? Did it hell? With Spectrum selling like hotcakes in the UK, the race was on for developers to replicate the success of arcade machines and in doing so overcome the limitations of the machine, which of course included those graphical limitations and the colour bleed caused by the way those attributes would clash when applied to game graphics, commonly known as colour clash. Colour clash wasn't unique to the ZX Spectrum, but it was the most obvious because in keeping the price of the system low, as little money as possible was spent on memory, and as little of that memory as possible was assigned to the job of the attributes. The next closest example I could find was the MSX system, which has 8x1 pixel attribute blocks as opposed to the 8x8 the Spectrum has, still a significant improvement. Although lazy coding would often see this artificially exacerbated when games were ported from the Spectrum to the MSX. And here are some of the methods developers tried to use to overcome those limitations. The first was to eliminate colour altogether, save for perhaps the borders, a technique adopted here by Last Ninja 2 and The Great Escape. No colour, no colour clash. The next method was to use large and colourful graphics, but limit their movements to large 8x8 colour resolution boundaries. Everything stayed within its boundaries, like this example, Light Force, and it looked great in screenshots on the back of cassette covers or in magazines, but of course movement had a blocky feel to it to work within those boundaries. Other developers just said, do you know what? Colour clash happens. And that's exactly what we got with Altered Beast. No attempt made whatsoever to try and mask the problem. And then, as seen here in Double Dragon, some games used full colour backgrounds and character scrolling, where the environment was scrolled 8 pixels at a time, but monochrome sprites were transparent, although they were drawn to stand out as much as possible. So those were the main tricks that developers came up with to present our games in light of the limitations of the machine. Some games were even polite enough to give us the option of how we wanted our clash to occur, with the background or the sprite taking priority, like this 3 Weeks in Paradise. These techniques served us well, and the advancement in the presentation of graphics from the launch of the ZX Spectrum to its death was significant as developers fine-tuned their processes. They even managed to beat the machine's 8-colour palette. The Spectrum allows a choice of 8 colours, 15 if you enable the bright bit in the attribute, giving a slightly different shade of that colour, not 16 because a brighter black is still black. the ZX Spectrum was used on televisions and not high-resolution monitors. As a result, adjacent pixels would in fact blur into each other. With this in mind, graphic designers would place coloured pixels next to each other with the intention of blurring them, causing the colours to mix and effectively giving a palette of 64 colours. This technique obviously put no additional load on the CPU and was used extensively. More advanced methods such as interlacing or alternating two screens between every frame interrupt were mostly restricted to the demo scene where the CPU didn't have the additional load of game logic. And the later 128K Spectrum did indeed include a shadow screen area usable for such a purpose. Other techniques involved paying careful attention to timing to modify the attribute area of RAM. By knowing precisely when the television's beam was at a particular line on the screen, the attribute RAM could be modified just before that line was drawn, giving the effect of different attributes for each individual line, effectively allowing you to break the 2-colour limitation per attribute block, giving you 8 times the colours. Many of these advancements were made long after the lifetime of the ZX Spectrum. Of particular note, the Bifrost engine, which brings improvements in the colour attribute system, giving you 2 colours in every 8x2 pixel block instead of the regular 8x8, by using the aforementioned beam chasing method. One could only imagine what would have happened if that had been developed during the machine's commercial lifetime. That wraps up our look at the ZX Spectrum's Ghetto graphics. I hope you enjoyed the video today. If you did, give us a thumbs up, subscribe, come back again soon, and thanks for joining me, Cave Dwellers. Take care.